Hey guys, hello everyone. So we are going to move onwards to the next topic in the physical chemistry series. So first of all, what are the types of unit cell? Now this classification is a basic classification. We are definitely going to move on to the Bravais lattice and so many things. But this is a basic classification. The classification on the basis of location of lattice points within the unit cell, right? So चलो बात करते हैं primitive unit cell, primitive or simple. Primitive means simple only, simple unit cell, simple cubic unit cell. This one, simple cubic unit cell. All right. So primitive unit cell में हम लिखेंगे simple cubic unit cell. All right. Now in this primitive unit cell, I would say that is the lattice points are present only at corners of the unit cell. Only at the corners of the unit cell. That is like this. Only at the corners of the unit cell in this way. Alright. Now for example, you have many different examples of simple cubic unit cell. Example, polonium. Polonium is one example. Okay. Now we move onwards and we talk about non-primitive. Non-primitive means non-simple. Okay. So non-primitive unit cell में आता है where the lattice points are present not only at the corners but also at different positions. For example, I'm directly writing this. Okay. For example, FCC, BCC. FCC is face-centered cubic unit cell. BCC is body-centered cubic unit cell. Then we have end-centered cubic unit cell. So all of these are examples of non-primitive, where you not only have the the lattice points at the corners but also at different positions in the system. Now before directly moving onwards, I have something important to discuss. When we are talking about a cube, because we will be needing this, so just write a little bit about the cube. So about the cube, a simple cube. What about the cube, guys? How many number of faces, or let's say how many corners are present? कितने corners होते हैं cube में? Number of corners. We are talking about the geometry of a cube. Let's understand the cube in a better way, then we move onwards. So number of corners are always 8. 1, 2, 3, 4, 5, 6, 7, 8, like this. 8 corners. Number of faces of the cube. So how many faces? 1, 2, 3, 4, back and front. 6 faces. Number of sides or edges. Number of sides or edges. This is what we call as sides or edges. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are going to be 12 sides or edges. Then we are going to talk about face diagonals. How many face diagonals? See, each face can have 1 and 2 diagonals. Each face of a cube can have 2 diagonals. So how many faces are there? 6. So 6 into 2 is going to give you 12 face diagonals. Alright. How many body diagonals? What are body diagonals? Which stretch throughout the body. So let's say if I'm drawing another cube over here. Now everyone has a different way of drawing a cube, right? So what is a body diagonal? Taking the exact opposite point. This point and this point over here is going to make one body diagonal like this. This point and the exact opposite, this point, is going to make another body diagonal. Then this point and this point, they are going to make another body. Okay, this was a little bit not so good. Let's try over once again. This is going to make another body diagonal. और कौन बचा है? देखो ये बच रहे हैं, ये दोनों point. So how many? It's not short. It is just looking like it is short, but all the body diagonals in a cube are of the same size. So how many body diagonals are present? 4 body diagonals are present in a simple cube. So these are some of the points about the cube. Now we are going to be needing this. That's why I discussed. Now we move onwards and see the non-primitive unit cell defined very nicely. Okay, in pictures. All these colorful pictures are very interesting. So yeah, so this was our primitive cubic lattice, or the SCC, simple cubic unit cell. Lattice points are present only at the corners. Lattice points किसको बोलते हैं? Once again, the ions or the atoms or molecules, whatever. Only present at the corners. Body-centered cubic unit cell. The lattice points are present on all the corners, 8 corners, yes, as well as one complete atom or one complete ion at the center. Body center मतलब cube के एकदम बीचों बीच. Okay. Now the lattice points in the FCC lattice. See, this is an FCC lattice. This was BCC. This is FCC lattice. So where are these present? Corners plus one lattice point at the center of each face. हर face पे एक एक और. So this is our right hand side face. This is our front face, top face, left hand side face, bottom face, and this is the back face. So there are 6 faces, 6 more atoms present on the face. That is the face centered cubic lattice. I have one more to discuss. For example, we are talking about end centered. So in the end center, definitely you will have the lattice points at all the corners. Okay, yeah. End center means two opposite ends. That is 2 opposite faces. Either it could be these 2 faces, or it could be these 2 faces, but only 2 faces, or back and front, but only 2 more faces. So corners plus opposite faces. Alright, where this is what we call as the end-centered cubic lattice. Then we have edge-centered cubic lattice. Let's not leave that out. So what is edge? Again, all the corners like this. Along with all the corners, there are going to be how many different edges or sides? 12 different sides. So I'm going to mark it with a different pen. This is one edge. On the center of one edge, another edge, another edge. 4 edges on the top, 4 on the bottom. These on the left and right. So how many edges? 12 edges. So this is edge centered. Edge centered cubic unit cell. So I would write here you are having the lattice points or the atoms at corners plus all edges. Okay, so you usually see the 4 types. You usually see this, 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 and this. type of unit cell. You don't see much of the edge centered one, but yeah, just for the sake of knowing. Okay, chalo, let's move onwards. And here comes the classification on the basis of axial length and interfacial bond angle. Okay, so here we are going to talk about different crystal systems. You don't need to draw and remember, but if there was a diagram, you will like understand it better. So let me just incorporate a diagram over here for all of you. Alright guys, so here's the diagram. Now classification on the basis of axial length and the interfacial bond angles. So we need to learn this axial length and interfacial bond angles because these are like some direct question. These questions used to be asked in IIT JEE, IIT JAM examination, but once in a while they have also been asked in your GATE examination and for 2 marks in CSIRNET also. So that's why we have to like remember the overall thing. So these are known as the Bravais lattice. They are mainly of 7 types: cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, rhombohedral. Okay, so what is the axial length? The length in all the direction, that is A, B and C, and the interfacial angle between the 3 faces. This is the alpha, this is beta and this is gamma. So alpha, beta, gamma, how they are going to be. So chalo मान लिया हमने this is going to be, for example, this is C, this is A and this is B. So A, B and C is going to be equal. For cube A, B and C are equal, तो हम यहाँ लिख देते हैं A is equals to B is equals to C. Alright, now what about the interfacial angle? This is alpha, this is beta and this is gamma. But for a cube all the angles are 90 degrees, isn't it? So alpha is equals to beta is equals to gamma is equals to 90 degree for all the interfacial angles are same for cubic system, and that's why this is mentioned to be the most symmetric cubic system that you can have. Okay, so for example, you have silver, copper, zinc blend, sodium chloride, potassium chloride, diamond. All of these are SCC, simple cubic system. Not simple cubic, it's a cubic system. And in our syllabus we are only going to talk about cubic only, but anyways let's move onwards to tetragonal. Tetragonal means, देखो imagine करो क्या किया, you just took the cube को लिया and hold on to this side, ये लो, इसको पकड़ के खींच दिया. I'm just stretching this one. So what will happen if I'm just pulling the cube like this on the upward direction, then it will become like this. This is tetragonal, the stretched form. ऐसे याद रखो, this is just to remember. Definitely that is not happening. I am just telling you to remember. So I am stretching this one up so that I get tetragonal now. The angles are still the same as the cube, but since you have done the stretching, one side has become unequal. So A is equal to B but not equal to C. And alpha and beta and gamma are all 90 degree. You know, I used to teach this trick when I was teaching for IIT JEE, but it still works. These are some of the examples. Orthorhombic. Now move onwards to orthorhombic. What am I doing once again? अब ये tetragonal has become a little bit unsymmetric. इसको भी मैं पकड़ के खींच देती हूँ. All the sides will become unsymmetric like this, but the angles are still 90 degree. So A is not equal to B, not equal to C. What I am doing is tetragonal I am stretching once, orthorhombic I am stretching again like this. So all the sides become unequal, but the angle still remains to be 90 degree. Alright, easy to remember like this. Cubic, then stretch once, tetragonal, you are stretching from above like this. So that becomes tetragonal. Then tetragonal you stretch one more time like this, horizontally. That becomes orthorhombic. Okay, then this is, yes, one more thing, cube से चले जाओ rhombohedral पे. What I'm doing to the cube, this is rhombohedral. This trick is my favorite. What I'm doing is, for example, imagine that the cube is like a jelly. So what you do, this is your cube over here. the base of the cube is stable, but the upper side you are pushing in one direction. When you push the upper side in one direction, it becomes like this, like a rhombohedral. So this was a cube, I am pushing it in one direction only. So the upper atoms have all been shifted and the lower are as it is. It becomes like a trapezium. So that is why rhombohedral. See what happens. All the sides are same. A is equals to B is equals to C, just like this one. But the alpha and the beta, they are all again the same, but they are not 90. Why? Because I have pushed the upper face. Okay. So this is how I get rhombohedral. Very easy. Will you be able to remember this? From cube, just push on the upper portion. It becomes like this, a little bit tilted. That is our rhombohedral. So this is a trick for cubic, tetragonal, orthorhombic and rhombohedral. Now what? Now we have monoclinic, triclinic and hexagonal. It looks like as if it is tetragonal or orthorhombic, but it is not. The hexagonal is not like that. First, draw a hexagon like this. Then, make the just draw the complete structure. Okay, draw the complete structure of hexagon in a 3D in this way. This is how your hexagonal system is going to be. You can make 2 out of the back also. I'm not going into the back. All I want you to understand is how I'm going to explain hexagonal. This is hexagonal. This system over here, this is hexagonal. Got it? So it is not a cube and it is slightly tilted. जैसे काजू कतली नहीं होती है. It's looking like a kaju katli in this way. Okay, so it is not a cube, it is not rhombohedral or anything, it is hexagonal, it is different. Or a cutout of a hexagonal system, just remember. So hexagonal mein kya hoga? These two sides, any two sides might be same, but the third is not going to be the same because this is like long. This is, let's say, this is A, this is B, but this one is C. So this is definitely different. So hexagon you understood now. A is equal to B, which is not equal to C. Very simple. Alright, but what about the angles? These two angles, this one over here and this angle over here, these two are going to be 90 degree, but ek angle hoga 120. Why? Because the internal angle, this one, this is not 90, this is an obtuse angle. क्योंकि काजू कतली देखा होगा तो वो ऐसा होता है ना, like this angle is not 90. So I will write alpha is equals to beta is equals to 90 degree. Two angles are going to be 90, but the gamma or any one of the angle, that is going to be 120 degree. Easy to remember. Hexagonal is cut out of a hexagon, but since we are talking about cubic type of system, तो इसलिए हमें cut out करना पड़ेगा, one side not same. So this is also easy to remember. Triclinic is very easy to remember. It is the most unsymmetric. सब कुछ cancel कर दो. देखो, this is not equal to B, not equal to C. Alpha is not equal to beta, not equal to gamma, not equal to 90. Okay, just like that. Triclinic is like this. It does not have like a very fixed shape. Everything is unsymmetrical. तो इसको याद करना बहुत easy है because this is most unsymmetric. Alright, most unsymmetric. What about monoclinic system now? Monoclinic again, guys, the last one to see. How can we imagine a monoclinic? Monoclinic is A is not equals to B, not equals to C, but the two angles are same. Alpha equals to beta is 90 degree, but the other beta is not 90 degree. The other beta is not 90 degree. Now, whether it is 120, whether it is 110, it could be anything, but it is not 90. तो इसमें इन दोनों में confusion हो सकता है आपको. You might get confused between hexagonal and monoclinic because the angles look similar. Because this gamma is not equals to 90 degree, but that doesn't matter because these sides are different. Monoclinic has a similar side, unsymmetric as compared to triclinic. इनकी side same है, but the angle is similar to hexagon. So you can remember it like this: cubic, tetragonal, orthorhombic. These three are having same angles. ये मैंने आपको कैसे बताया था? You have got a cubic. Now you stretch from one side, that becomes tetragonal. One side becomes unequal. Then you push from one more, pull from horizontal side. Then all the sides become unequal, but the angle remains the same. Then cubic को लेकर जाओ, just take the cubic and tilt from one side, that becomes rhombohedral. So all the sides are same, but the angle are not 90. They are still the same, but they are not 90. Hexagonal, I have shown you, draw a hexagon and then cut out a system from over here of 8 corners. So this is like a kaju katli. So this is going to have two sides same and the other different. Two angles are 90, one is the 120 degree. Okay. A triclinic is the most unsymmetric system. Anything is not same. Monoclinic ka axial length is same as triclinic, but the angle is similar to hexagonal. Okay, just don't be like very sure कि इसका पूरा angle same है, because gamma is not equal to 90 बोला है, and here it is precisely 120. So that is a slight difference. Okay. So just take care of that. Now these are some of the examples that I've given you. I think that this table is good enough with diagrams, with examples, and with the axial length and bond angles, everything. Okay, so now we are going to move onwards and we consider the contribution of atoms or ions in different type of unit cell. Okay. So yeah, contribution of atoms or ions in a unit cell. So let's see what's going on. We have a primitive cubic metal unit cell, मतलब कि ये हो गया SCC. So in the SCC, as I told you that we don't have lines. If I'm drawing a cube, let's say they have drawn a cube like this, they are only showing few of the faces, not all. Okay, not a good cube, but anyways. So these are not actually lines. The lines are actually imaginary, where I'm imagining they are just the internuclear axis of the adjacent atoms. Okay, so the unit cell is actually like this, that this edge is having this part of the atom situated on it. The thing is, the most important part is you have to imagine that when I'm talking about the corner, the corner like this one, how many different unit cells are going to share this corner? So only one diagram I'm going to draw, because definitely in this one diagram you will be able to understand. Okay, so this is a side cell. The cell is on the right hand side. So this is a side cell which is sharing this. So it is divided in between two. Now if I draw one more in the front. Alright, so one more in the front is going to look like this. So what happened? It is being shared between 1, 2, 3, 4 different unit cells. If I try to draw all of these things on the top, if I'm trying to draw this unit cell on the top, then all the 4 are going to come on the top also. I know it is going to become a little bit messy, but this is important to imagine that the unit cells on the top, they are also like this. So the 4 unit cells on the bottom and the 4 unit cells on the top, all of these are sharing that particular atom on the corner. So how many? 4 plus 4 is 8. So that corner atom is being shared by 8 unit cells. So each corner atom, so in the SCC you only have 8 corners, and each corner atom or ion is being shared by 8 different unit cells. So एक unit cell में कितना आया? 1/8, isn't it? So if I say that only this unit cell is having how much of that corner atom, it has 1/8 of the corner atom. So how many corners do you have? You have 8 corners. So 8 into 1/8 is going to give you the actual number of how much atom is present in that particular unit cell. So you have only one atom per unit cell. One atom per unit cell in a primitive or a simple cubic lattice. Okay? Again, we move onwards and we talk about body center. So in the body center, as I've told you, draw the complete lattice, one complete atom at the body center. It is like this. Then how many atoms totally? So total number of atoms, that is equals to 8 into 1/8 plus 1 complete at the center. कितना हो गया? 1 plus 1 is equals to 2. 2 complete atoms per unit cell. In the face centered one, what are we going to take? We have again total number of atoms, that is equals to 8 into 1/8 plus on the face. So if there is a atom on the face, you see that this is cut into half. So that atom at the face is divided in between two different cells. So 6 into half is going to be 3. So 1 plus 3 you are going to get 4. 4 atoms per unit cell in FCC lattice. Alright. So this was about simple SCC, BCC and FCC. If you want to talk about the end centered one, वो भी देख लेते हैं. Alright, these are no more just points, these are atoms. Okay. So yes, like this. So on the opposite two ends. So 8 into 1/8 plus कितना होगा? 2 faces है, तो 2 into half. So 2 into half is going to give you 1 again. So this is going to be 1 plus 1, 2. This is same as BCC, but the arrangement is different. What is this? End centered. Now, if a questioner is asking you what are the total number of lattice points, अगर उसने number of atom नहीं पूछा, they are asking you number of lattice points. What will you say? In the SCC, number of lattice points मतलब कि at how many different points your atom is present. So here totally they will be 8. Alright, for the SCC. For the BCC, 8 plus 1, it is going to be 9 because I'm writing this in the black color. Okay. Then you have FCC. So you have 8 corners, 8 plus 6 faces. Because definitely the atom is present at so many positions. So 8 plus 6 is equals to 14. Then comes the end center. End center means you are having 8 plus 2 more. This is equals to 10. So the black ones are all the total number of lattice points which are present. Okay. Very well. Now we move onwards. So now it is time to talk about how many different types of close packing of atoms are possible. Why are we discussing close packing of atoms? Because we need to see that in how many different possible ways the atom could be arranged so that we get a lattice. ठीक है? तो उसमें भी possibilities है. What are the possibilities? Let's see. First possibility I'm talking about in one dimension. One dimension means only one axis. So just place the atoms close to each other on a one single axis, x-axis for example. ठीक है? Fine. In two dimension, x and y axis, how many possibilities are there? So let's say this is your x-axis and this is y-axis. So I have placed these atoms. Look at the centers. The centers of these atoms coincide. तो यहाँ पे क्या बोल सकते हैं हम? In a simple cubic lattice. This is known as SCC. Simple cubic lattice in 2D definitely. Here the centers of atom coincide. This is how they are placed. Okay, that is going to form a cube. If you see, just add all of them, all the centers, you are going to get a cube or basically a square. अच्छा ठीक है, इसको हम simple cubic नहीं, इसको हम square lattice बोलेंगे because definitely it is in 2 dimension. So we call this a square lattice. We call this a square lattice because the centers are forming a square. Fine. Then I have one more type of arrangement. What if I'm just shifting this line a little bit and putting this in the depression of the upper one? इसको क्या बोलते हैं? इसको बोलते हैं in the second layer. See, in the second possibility, I am putting the atom in the depression of the first two, of the first layer. ये first layer है. And this second layer, atoms are placed at depression of first layer. Depression means where there is a space. यहाँ पे जहाँ पे ये space था वहाँ पे. So I'm placing it like this. Now third on the depression of the second, fourth on the depression of the third, like this. If I arrange the atoms in this way, then I see if I just take the centers and add all of them, I will see it forms a hexagon. That's why it is known as HCP, hexagonal close packing in 2 dimension, in 2D. Okay, so let's continue this in 3D. 3D matlab ki you have done the same in 2D. Now you extend this in the Z axis also. So this is what you have done in X and Y axis. Extend this into the Z axis, like out of this screen. Okay. So in one possibility, we can place the second layer in such a way that the spheres of the second layer come exactly on the top of the first layer, जो मैंने यहाँ पे किया था. So this is your square lattice, like this. Just place the other one exactly at the same. So just the square lattice is going to continue. That will become the cubic lattice. Second possibility is the sphere of the second layer placed on the depressions of the first layer. So just this one, जो हमने यहाँ पे किया है, if I'm just extending in the Z axis, I will do the same. These are the depressions, these. So I will place the next layer on the depression on these points. ठीक है? So let's talk about this. It's very interesting. See. Now what I'm doing is, I've taken HCP because you see they are already in the depression. I've taken HCP. So HCP से हम क्या कर सकते हैं? The 2-dimensional HCP. These are the depression. The yellow depressions are different and the red are different. Why are they different? Because if you place a atom on the yellow, if you continue the yellow line, place the atom on the yellow points, that is going to give you a different line. If you place it on the red points, that is going to give you a different packing. So just stay calm and listen. So if the next layer or the blue balls I am placing on the yellow depressions, that is going to give me something like this. This is the second layer. Alright. I've done the same thing over here. Second layer I've done the same thing. Yellow points के ऊपर second sphere I have placed. Very good. Now just think of this diagram as a continuation of this one. ये नीचे जाएगा तो ये आएगा. Now again I have placed the third line on the yellow depressions only, because you see these and this one, they are going to be coinciding. इसको हम बोलते हैं AB packing. So there was a line A, the line B was on the depression of A, and line A again is coming, which is going to be on the depression of B. So these AA atoms are going to be exactly on the top of each other. इसको बोलते हैं AB kind of stacking. This is known as AB kind of stacking. However, I have done something different on the other line. ये जो red depressions है ना, the red depressions, here I am placing the third one. Now this third one is different. It is not going to be exactly on A. ये देखो, this A was there. B is on the depression of A. Now this A again I'm placing on the depression of B, which is exactly, the atoms are exactly, A and A are exactly on the top of each other. Right, but the C one over here is not exactly on the top of A. This is A, this is B, and C are not on the top. These are on another depression of A. So these will make two different type of close packing system. ये जो ABAB system है, the ABAB system is the hexagonal close packing. This ABAB system is the hexagonal close packing system, and the ABC is the cubic close packing system. This is what you have to remember. Given that the close packing of equal size sphere we are considering. So these are equal sized sphere. So what I'm doing is, this side of the diagram is this, okay, for the ABAB, and the other side is for this one, okay. So now it is very clear that what is HCP close packing in 3 dimension and what is CCP close packing in 3 dimension. Cubic close packing is CCP, HCP is hexagonal close packing, ABAB and ABC respectively. Okay, very nice and clear. Now we are going to talk about voids. It is going to take a little bit of time to understand, but this is very, very important. Alright guys, so now let's talk about the voids. So basically we have understood that what are the lattice points and how the lattice points are present in every different type of lattice. Alright, so now we are going to take that knowledge and understand what are the octahedral as well as the tetrahedral void. So basically look over here guys, voids are nothing but empty spaces. Alright, empty spaces with respect to whom? Empty spaces with respect to the atoms which have already occupied the lattice. So for example, I am placing, see when we were talking about the one-dimensional, two-dimensional lattice, so on and so forth. So I showed you that when I am like placing these atoms all together and placing the other atom, the other layer, the second layer into the depression of the first layer like this. Still there was some void, like a triangular void, as you can see in 2D. So this is a two-dimensional diagram that I have drawn, like roughly placing across the x and the y axis. Alright, so you see that there is a triangular void. Void is an empty space where the atoms are not occupying that site. So if I take this into 3D, you have already seen the HCP and the CCP close packing. So by now you should know that whenever you are occupying one particular depression with another atom, see this is a layer, for example, the two-dimensional layer. But now I want to place one atom on the depression of the other atom like this. This is my top layer, for example. Then what happens? If you can see through that atom, you will see that still there is a void, even though you are trying to do the maximum most efficient arrangement. That's why you are keeping another atom on the depression of that particular void, but there will still be some space which is not occupied by the atoms. That empty space can be classified into two types based on the shape which is created. So when you are placing these kind of 4 atoms, then the think with respect to the void. So when I'm thinking with respect to the void, the void is surrounded by 4 different atoms. Alright, so when the coordination of the void is 4, just write it down. When the void is surrounded by 4 different atoms, then the void is going to have a coordination number of 4. Then it is going to be known as a tetrahedral void. Very simple. Coordination number 4 है तभी tetrahedral है, right? So whenever we are having a lattice arrangement where the void is going to be surrounded by 4 different atoms, it will be known as a tetrahedral void. Similarly, if I have this kind of a layer placement, that is this way, this is how I arrange. Now the second layer which is placed is going to be in a different manner. How? Let's see. The second layer is going to be placed like this. So it is still on the depression of the first layer. If you see the black one, it was forming a triangle, inverted triangle like this, the black one. And the blue one, they are forming another inverted triangle like this, right? So the space which is present is actually surrounded by 6 atoms. There is definitely a void present over there, and that void is surrounded by 6 different atoms, right? चलो different नहीं बोलते हैं क्योंकि all the atoms are same only, by 4 atoms. So when the void is surrounded by 6 atoms, then the void is going to be known as, it is going to have a coordination number of 6, it is going to be known as a octahedral void. Okay, so this is the basic classification of a void, basic definition of a void. Now, how many octahedral voids do we have in a particular lattice or the tetrahedral voids? ठीक है, तो देखो guys, first of all, how many in a simple lattice, for example, I'm taking just for example, I'm taking FCC. ऐसा नहीं है कि सिर्फ FCC में ही होते हैं voids. It happens in BCC also. It happens in simple cubic also. Every kind of lattice will have some voids. So I'm taking FCC just for example. Okay. So अब ये बताओ that how many number of atoms are present in FCC. So when I say how many number of atoms are present in FCC, I can also say what are the lattice points, because lattice points को हम number of atoms ही बोलते हैं. So lattice points, how many lattice points or number of atoms are present in FCC? It is denoted by Z. So this is going to be 4. We have already found that out, right? Represented by Z. Now, if we see if there are 4 lattice points in FCC, where are the octahedral and the tetrahedral void? तो ये देखो याद रखना है, the octahedral voids, these are present at the body center. The octahedral voids are present at the body center plus the edges of the unit cell. That is, ये देखो, these are the octahedral void. For example, this is our normal FCC lattice. ये हमारा FCC lattice है. Okay, where we are having the lattice points at the corners as well as all the face centers. So when you see कि सारे face centers को हमने मिला दिया, this is one face center, this is another one, this is front face, this is bottom face, right face and the back face. So when you see that all the face center points are combining to create a hollow, that hollow has a coordination number of 6 because 6 atoms are surrounding that hollow. इसीलिए वहाँ पे body center पे octahedral void आएगा. So this void at the center over here is going to be an octahedral void. So where are all the octahedral voids? See देखो, on the edges, because you know the edge is shared by different lattice, right? So एक unit lattice के surrounding में और भी unit lattice होते हैं, right? So this one is surrounded by at least 4 different lattices. So 4 different lattices में और भी atoms आएंगे, 1, 2, 3. There is going to be one more, 4, and let's say 5, and let's say 6. हो गया 6. So this one is also surrounded by 6. Again telling you 1, 2, 3, 4. One more over here, the face of the upper one, the face of the right hand side. Only these 2 you have to consider, right? So these are going to give you a coordination number of 6. So octahedral voids are present on the edges. These are all the edges that I am marking once again. ये सारे edges है. Okay. Which edge is left out? ये वाला edge बच गया है. यहाँ पे एक और mark कर देते हैं. This edge, the front or the bottom, whichever you consider. And a body center. This is a body center. Okay. So octahedral voids are present at the body center and the edges of the unit cell. Alright, fine. Now we move onwards to another one. That is, अच्छा ठीक है, एक बार ये भी देख लो. बॉडी सेंटर तो एक एटम होता है पूरा. Edges of the unit cell कितना होता है? One of the this atom which is present on the edge is going to be divided into 1/4 because it is going to be surrounded by 4 different cells. One over here, then over here, then one more, 4. So कितना होना चाहिए? There are 12 edges. All right. So 12 multiplied by 1/4. How much are you getting? 1 plus 3 is equals to 4. So what did you realize? Lattice point was 4 in FCC और FCC के octahedral voids भी 4 ही है. So actually the number of octahedral voids in any kind of lattice is equal to Z. मतलब कि जितने भी lattice points होंगे उतना ही number of octahedral void हो. Right? Now we move onwards to tetrahedral void. In the tetrahedral void, it's a little bit tricky to explain, but let's see. You have to write this first. Each tetrahedral void is present exactly between the corners and the body center. All right. So since it is a tetrahedral void, वो surround होगा 4 atoms से. So I can also write each tetrahedral void is surrounded by 4 atoms. It is surrounded by 4 atoms. All right. Now in these 4 atoms, one atom, or let's say one is present on the corner, plus the other 3 are present at the face centers. 3 present at the face center. इसका क्या मतलब है? Let's talk about this face center. So trying to find out the tetrahedral void is a little bit tricky, but let's try to understand. You have just drawn a FCC lattice. FCC lattice में क्या होता है? You have corners पे atom होता है, and then you have the atoms at the face center. Let's draw the ones at the face center. सारे draw करते हैं. Top, right, left, bottom, front face, and the back face is also there. This is not body center, that is the back face. Okay. So this is how the face centers are present, and this is our simple FCC lattice. Now where is the tetrahedral void? The tetrahedral void is exactly between the corners and the body center. इसका मतलब क्या हुआ? Do you have to take the BCC lattice क्योंकि उसी में body center होता है? नहीं. No. We are just drawing an imaginary body center. Look over here. Just imaginary body center. There is no atom at the body center. I'm just marking the body center so that you can understand where the void is. So exactly between the body center and this corner is a space right over here. Okay, this is the void. It has not been marked. अभी मैंने mark किया है. Now this void is surrounded by 4 different atoms. How? 1 at the corner and 3 at the faces which are common to it. कैसे होगा common? देखो, this is present over here, मतलब कि ये body center है and this is the corner. Alright, so it is present in between that. So what are the faces common to it? The left hand side face, the bottom face and the front face. This is the front face. ये तीनों इसके common आएंगे, closest to it. Okay, so that is how the tetrahedral void is shown. Now if we move onwards and if we try to show all the tetrahedral voids without worrying about the FCC lattice, then it is going to appear like this. So this is our body center, alright, and this is one corner that I am considering. दोनों के बीच में ये रहा tetrahedral void. Then this is our body center. You consider this corner, so this is your tetrahedral void. This corner, the body center, this is your tetrahedral void. This corner and this body center, another tetrahedral void. This corner, body center, another one. This corner over here, backside, and the body center, this void. The front one again, this side, and this is your body center, so this is the void. This one is going, this corner is going to have from the body center this void. तो ये सारे सिर्फ voids है. These are only the voids. Now, when these are only the voids, you have not counted the face centers. But let me do so. Face center यहाँ पे लगाना जरूरी है. क्यों? Because then only you will be able to show that how they are forming a tetrahedral system. So see, I am putting one face, one corner over here to this void with respect to this void. I am placing the face centers, one on the top, the other one on the back side. ये back face है, ठीक है, back face का center, and the one over here, for example, ठीक है. So this tetrahedral void is going to be surrounded by how many different atoms? One over here, another over here, another over here. ऐसे ये बन गया है एक tetrahedral space. Alright, so this is one tetrahedral void surrounded by 4 different atoms. So show all the face centers and then try to figure out, but you have understood how the tetrahedral voids are going to appear. Okay, that is the more important point. ये tetrahedral void है और ये octahedral void है. So yes, I hope that this is clear to all of you. Now one more thing is, if you have noticed कि अगर हर atom और कॉर्नर के बीच में, see, every body center and corner के बीच में, if you are placing a void, then how many voids are present in total? You see 1, 2, 3, 4, 5, 6, 7, 8. So these voids, actually the tetrahedral voids, are twice the times of any lattice point. क्योंकि यहाँ पे 8 हो गया, 2 into 4 for FCC gives you 8. So octahedral void is going to be equal to the lattice point, but tetrahedral void is going to be twice that of the lattice points. ठीक है? For FCC the lattice point is 4, so that's why tetrahedral voids are 8. Alright, now here comes an application of understanding the tetrahedral void. What is that? एक application ये है guys कि जो diamond cubic lattice होता है, diamond cubic crystal system, that is very nicely explained when you understand the octahedral tetrahedral voids. Okay, तो चलो diamond का lattice consider करते हैं. Alright, so what and where the atoms are present. So let's write over here the lattice points on in diamond. The lattice points in diamond are present at the corners, all of the face centers, all the face centers, and half of the tetrahedral voids, and half of the tetrahedral voids. So half of the tetrahedral voids means that is going to be equal to the lattice points. पर इसका मतलब ये नहीं है that you say कि मैम octahedral voids are also equal to the lattice point, तो हम वहाँ पे place कर दे क्या? No, you cannot do that. It is present in alternative tetrahedral voids. Okay, so for the diamond, the atoms are present in alternate tetrahedral voids. So let me show this to you with different pen colors. This is the diamond lattice. All the corners I am filling out with black. So these are all the corners. These are all the corners. How many corners do we have? We have 8 corners. Okay, तो ये हमारे पास में हमें 8 corner find out करने हैं. These are all the 8 corners that I'm talking about. This one and this one as well. So I'm putting black color as corners. ठीक है. Then I am putting red color for the face center. This is one face center, and let's say this is another face center over here. Back face, and this is the bottom face, और लेफ्ट हैंड साइड वाले फेस में हम इसको ले लेते हैं. ओके, नाउ अज्यूमिंग दैट देयर आर 8 tetrahedral voids, because face center पे आया तो DCC actually becomes FCC only, right? So where are the tetrahedral voids? In between, they are going to be in between the body center, just marking a dot for the body center. There is no atom at the body center. ठीक है, in between the body center and the corners. तो अब ये body center और ये corner पे एक tetrahedral void आया. Okay, this dot as well as, see, I'm talking about alternate, क्योंकि half of the tetrahedral voids are going to be filled. तो अगर half हो गया है, then we can say it can be filled up in an alternate manner. In an alternate manner also. ठीक है. So I'm skipping the tetrahedral void for this corner and I'm moving on to the next one. इस corner का tetrahedral void है ये वाला, right? Then similarly I'm skipping this corner, I'm taking this one. This is the tetrahedral void. Then I'm skipping this corner, no tetrahedral void consider, I'm considering this corner. So कितने हो गए? Half of tetrahedral voids. Alright, so the blue ones over here, these are the tetrahedral voids, and the red ones, those are the FCC, face centered points. Face centered points. Alright, so this is how the diamond lattice is present. And guys, if I had to draw it, I would not make this perfect adamantine type of molecule. See, if you can imagine, this is actually the adamantine structure. Alright, so that is considered to be the monomer of a diamond lattice, and it is exactly placed in a cubic cell. So ये कितना अच्छे से represent किया हुआ है, that's why I took this diagram. Okay, so now we will find out how many lattice points are present in DCC. तो चलो कैलकुलेट करते हैं Z वैल्यू. Z वैल्यू फॉर DCC is equals to how much? It is saying कि all corners पे lattice points are present, so 8 into 1 by 8 for all the corners. All the face centers, 6 into half for all the face center, plus half of the tetrahedral voids. How many tetrahedral voids we have considered? We have considered 4. Alright, half of the tetrahedral voids. तो face center पे कितना होना चाहिए? 4 होना चाहिए. 4 into 2 is 8. So I'm doing half of the total tetrahedral void. That's why half of 8. How much do I get? 1 plus 3 plus 4. That is going to be 8. So you see, in one unit cell, you are having 8 atoms. That is why the diamond is the hardest lattice. Alright, 8 atoms per unit cell. Okay, very beautiful. Alright, this is how you understand that the diamond lattice is going to be. अच्छा देखो एक और चीज, since there are less tetrahedral voids over here, you can understand one more thing. The upper tetrahedral voids will always make a W. Upper tetrahedral voids, they will make a W, and the lower tetrahedral voids, they are going to make a M like this. So you see, यहाँ से consider करो, go down over here, then at this face center, then again tetrahedral void, then at this corner. ये W बना रहा है ना? And then go down this corner, tetrahedral void, face center, tetrahedral void, corner. It is making an M like this. So this is one method of correctly drawing. Just a confirmation कि हमने सही बनाया है. Okay, for the voids.